us start the last session of the Leçon Jacques-Louis by Professor Alfio Quarteroni. So who will continue his lessons on with the following title, From Problem Setting to Problem Solving via Scientific Machine Learning. So please, Alfio.
Thank you very much.
Very glad.
Let me once more remind you what is the.
Il faut que tu cliques sur le PDF.
Ouais.
Tu cliques dessus simplement. Et ensuite, ça repart.
Okay, très bien. Okay. Where we stand, we have seen this picture 2 or 3 other times. So I've been in the first day covering this branch here with the setting and development of mathematical model that is inspired by physical problem. The physical problem, the driving physical problem is the simulation of the heart. And then you see the numerical models. So this is, let me just to oversimplify, this is just human intelligence, or say science-based development. What you have on the right-hand side is instead all what is driven by data. So you have data, and you don't even know which kind of process generated those data. You just don't know, take those data and you want to extract knowledge from it. This is the philosophy of machine learning algorithms. And I tried to give you yesterday kind of a global picture, say mathematical picture, where you see the role of data, the role of machine learning algorithms, the role of neural networks, and some mathematical results and mathematical theorems that tell us which kind of accuracy we should expect, and which are the main drivers to set up the architecture of the world. That's the idea, right? So as I told you several times, I believe that the best opportunity is here, where you try to combine these approaches. And again, philosophically speaking, this is a kind of obvious remark. Every time that you have a new technology in a broad sense, that comes into play, and the very first reaction is to say that I don't need it. Second reaction is that, of course, you think a bit more. You think that you may develop a more opportunistic point of view, and therefore try to take advantage of this. This has always been the case in the history and the evolution of science. So how can we devise algorithms or approaches that see here? And this is what today is often called scientific machine learning. It's not a definition written in the rock. Actually, there is no mathematical definition. That's just an idea, right? And indeed, the definition that exists are not, well, it's not a unique definition. And here are some examples out of many other examples. So in the DOE report, DOE, you know, is the Department of Energy, and the Department of Energy has other departments in the United States. They think about new scientific developments, and they try to end up with providing precise guidelines. And this is the definition that they gave. Scientific machine learning is a core component of artificial intelligence and a computational technology that can be trained with scientific data to augment or automate human skills. So it's not actually a definition, it's just, say, a remark, right? So augment or automate human skills. And then this is another one that was used at Brown, at ICERN. ICERN is a research institute at Brown that hosts, like Oberbolfax, and hosts different types of conferences. Scientific machine learning is a merge of computational sciences and data-driven machine learning. Here it is, right? It's a marriage of the two things. Implemented in software is a set of abstractions to leverage existing domain knowledge and physics model with learning schemes and accelerated computing platforms. And then there's another one that I also like, is contained in a book, little book by Will Skilders. And he says, scientific machine learning is a combination of scientific computing and machine learning, combining mathematical models with data-based reasoning, presented as a unified set of instructions in the high-performance implementation, and so on and so forth. So, graph, right, is just all possible ways you can try to take advantage of the combination. Now, I think that we have to set ourselves in the context, right? And today the context is the one where people believe, or many people believe, that you can do everything with machine learning algorithms. But in fact, this is not the case, right? And there are obvious arguments. You see, you have stunning results that have been obtained in machine learning algorithms when you process large data of volumes, large volumes of data, say, and this indeed is a task that our brain find very difficult, very painful. And there's too many data, our brain is not capable of extracting relevant knowledge from all those data. However, you want to read those data and go through those data using some a priori knowledge, if you know what you're talking about. And this is the problem, right? The problem is the interpretation of the critical, say, approach to the data. And this critical approach is available provided you know the field, you have prior knowledge. And if you have a prior knowledge, why not to use it? Why just ask the data to derive any possible, say, information? So this is the idea. So the standard approach would be observe, ask a question, develop a hypothesis, make prediction, and compare with experiments. And here we want actually to, you see, iterate on this procedure in order to inject our own knowledge. So this is the setting of the problem, I would say. If you want to be very lazy in terms of, say, being a bit dogmatic, you can think that when you know a lot of physics, you need few data. If you have to solve a PDE, if you have to solve a heat equation, or whatever equation you have in mind, right? How many data do you need? The right amount of data. Initial conditions, boundary conditions, coefficients, and that's all. You don't need more data. Even though you have more data, you cannot use them. Otherwise, your problem will be overdetermined, right? And if you have fewer data, we'll have infinitely many solutions. So you need the right amount of data, no more, no less, right? So if you have a small data regime and you know a lot of physics, well, this is where you use, say, this is base model. If you have no physical insight, this is the other extreme. I'm observing a phenomenon and you know anything about the physics of this phenomenon. Well, when I talk about physics, I mean the real world, and it could be medicine, it could be biology, it could be, you see, whatever kind of problem, environmental science, and so on. So if you don't have any physical knowledge, then you need big data, right? So you see that the two arrows go to different directions. So data and physics are somehow complementary in this perspective. So how can you develop scientific machine learning practically? What can you do? How can you combine the two approaches? Remember, the two approaches are called DM, digital models, physics-based, and machine learning, data-driven, okay? So you can use your knowledge and inject it into the machine learning algorithms. Okay? So in this case, we have in the end a machine learning solution, but it will be informed by digital models. So we want to empower machine learning application with a deeper understanding of the problem structure when you know the problem structure. This is one philosophy. Right? The other one is the other way around. We want to use machine learning to, say, exploit availability of more data, even if you do not know all the data. Sorry, you don't need all the data because you know, remember, when you have PDE, you have the right amount of data. Right? But you have more data, you may want to use that to enhance the descriptive properties and the efficiency of the physics-based models, and we'll see examples, right? Again, you may want to use machine learning algorithms into your digital models, into your numerical approximation, to navigate through physical environments characterized by extensive two-dimensional, multimodal data streams. What is a multimodal data stream? You may have data that comes from different sources, come from social media, from observations, from any possible sources, right? They could be real numbers, they could be movies, they could be any kind of, could have any kind of form. And then again, use digital models to empower machine learning algorithms when you want to somehow maximize their impact in science and engineering. And we'll see examples. So the goal is support scientific goals of discovery and understanding, and underpin decision through prediction, optimization, and then quantification. Those are keywords that we find several times when we try to combine, when we actually combine the two things. I think I've already shown this picture. These are the two different words, and these are many possible ways you can make a coalescence of these two words. Right? These are two drops, and why not try to get a single drop? And then you can do it in many different ways. For instance, you can use physics-based models to regularize the loss function that you have when you have to use data-driven models. To avoid overfitting, remember, overfitting is a big fact here, because overfitting basically means that you have so many data that when you train your model, you may spend too much time by, say, looking at the very fine details of the data, but since those are affected by noise, maybe what you get in the end is something that cannot be generalized easily to other data. You may want to feed the learning process. What does that mean? Well, it means that in fact, most often you do not have big data. Sometimes you have scarce data, even in data-driven models. For instance, if I want to go on Mars and I need data to develop my, say, simulation method to find the right trajectories and to resist the change of different density in the atmosphere. I mean, I do not have data because I cannot make experiments. This is hypersonic flows in atmospheric conditions, stratospheric conditions that are not easy to replicate on Earth. This is a case where you do not have data. But more practically, forget about maths. To take any application in medicine, I mean, having data means that you have to ask people to undergo very severe exams and very costly exams. Now, if you go to a hospital, you say, well, look, I will need data from 100 patients because you want to feed my model with, if those patients are not, say, if they are healthy, there is no way you can get those data. Right? Because this, even if you go and you pay, because you have a big reserve grant, I mean, doctors will not, hospitals will not let doctors to take those exams for people who are not in pathological conditions that require most kind of exams. So typically in machine learning algorithms sorry?
Especially if you're not dead.
Yes, absolutely. Well, actually, we have examples like this for the, you see, for the grid, and I have a personal experience in one of the biggest hospitals in Milan. They had in the very first, say, weeks, you know, there's been an explosion of COVID cases in the northern part of Italy. And so they had in a couple of weeks, some 3 weeks, some 30,000 people going to the, you see, to the hospital because they were affected by COVID, or say that they were feeling very bad, and that hospital could not host all of them. They could not treat all of them, right? And in the end, they've been good enough to develop a machine learning algorithm. And they're setting a machine right at the entrance of the secure, how do you say, Protocols, right? Yeah, this is the right English translation. So, and this machine learning algorithm was able to basically, input output, right? What is the input? The input was the guy who was in front of the machine and he answered 4 or 5 basic questions. How is your temperature? How can you breathe? And so on and so forth. And the output was green, yellow, or red, right? Green means go home and just relax, and we'll see what is the evolution. But for the time being, there is nothing to be worried about, right? And red means you stay here, and you have to host you immediately, right? Immediately, and yellow was, well, you just stay here for a couple of hours, and then we'll see how you react, and we decide whether or not we keep it. So they've been able to treat those, cases in a very efficient way in a situation that was really traumatic, right? So and they didn't have data in those. Here, example of scarcity of data, and another example of scarcity of data when you have, let's say, some people affected by severe, for instance, heart pathologies or liquidation of and so those are cases where you do not have enough data to train your neural network. So what can you do in those cases? Assume that you have a digital model from the hub, you can produce many solutions. Of course, it takes time, but you can produce many solutions that can be used as data to train the machine learning algorithms. That's a very classic case, right? So you use digital models, physics-based models, to generate data that will be used as training data for the model. Okay, this is feed the learning process by new data. And so on and so forth. And the other way around, well, we'll see, you have a new material, you want to carry out that, say, develop a model, mathematical model for a large deformation or whatever, and maybe you do not know the constitutive law of the material. So what can you do in this case? Right? You have divergence of P of U equal to F, P is the calculation stress, and then you need a strain stress relationship that you do not know because this is the material, for instance. So what do you do in this case? Well, for instance, you can use machine learning algorithms not to find out the new constitutive law, but to find out, say, point to point, the way you go from stress to strain, right? For parameter calibration, sensitivity analysis, to reduce the dimensionality of the problem. Those are examples where you are actually using, say, this side into that side. Right? So those are just titles that you can now identify situations and context. So to be a bit more specific, here is the way we can use digital models, so physics-based models, to help data-driven models. So assume that you only are here. This is a classical machine learning setting, right? You have experimental data. Out of this data, you create a training set, and then maybe you also have a testing set and a validation set. You develop your machine learning algorithms, and you have a solution. And remember here, solution means it's not a solution of PD. It's an input-output function. So those data you want to retrieve information, right? And here are several possible ways where you can use digital models. For instance, FOM stands for full order model. You have a PDE, you know the process. You have, for instance, a numerical model like finite elements or whatever, what engineers call a full order model. A full order model is the best that you can do, right, in the field for a specific problem. You can use the full order model to generate new data to feed the training system. This is a very classic context. Another context, you want to reduce the dimension of the problem, and you use the autoencoder. Now, autoencoder telling you what it is. Another example again, remember this P, we talked about P in a while. P stands for physics informed neural network. So you want to inform your neural network of physics, of the physics behind this. Right?
So if you know the physics, I want to inject this knowledge into my neural network model. And in the end, I will have a data-driven solution. So it's not a data-driven solution. This is a data-driven solution, but it will be informed by, say, your knowledge of the physics. And you see, you can use both the mathematical model, we'll see why here, or the numerical model to help your, say, data-driven solution. And here are, say, the example that when you will do that of courses for our articles, you will see. On the other side, assume that you have complete knowledge of physics, or almost a complete knowledge of the physics, then you have a mathematical model. So you have data, and data write the data that you need, initial condition, boundary condition, coefficients. Then you have a mathematical model, PDE, say, numerical model, and then you have a solution, like a complete solution, complete understanding of your problem. So how can you use, in this case, machine learning algorithms? For instance, you don't have enough data. What do? You don't have boundary conditions, or you don't have boundary conditions on a part of the boundary, right? Now, if you want to use a mathematical model, you are stuck. You don't have condition, or you miss the coefficients, which is very often the case. If you have a patient-specific application, you miss the coefficient of the specific patient. Some inconducibility or position of the fibers, these are many other kind of coefficients. So the coefficient for the ionic model at the cell level, that's very, very often the case. So you miss the coefficient. You don't have constitutive laws. You want to learn the dynamics, which is hidden in your process, and you don't have enough elements to understand, right? Or you want to reduce the dimension of your problem. Remember what I was saying 2 days ago, you have for 1 second of physical time for a single heartbeat, it takes 4 hours on a big supercomputer, and you want to reduce. So how do you go from say 700 billion variables for a single heartbeat to 100, 1,000 in order to be able to solve it real time? So that's another case where machine learning algorithms can be helpful. So you see already the interplay between the two approaches. All right, let me now try to be a bit more concrete and consider a PDE and see a couple of examples, right, of this general philosophical approach. So when you have a PDE and we use, forget about visual intelligence, just go with the classic approach. So a PDE, you have, for instance, a numerical method you trust. So there are questions that you typically ask yourself and for which we have an answer, because you have theory that has been developed since the last century, right, the middle of last century. So how reliable an algorithm will be for a given type and quantity of data? We want the reliability, we want to trust on this model. Okay? How robust is the solution with respect to variations in data or additional noise? This is stability, right? You want to see you are a method that is stable with respect to the variation of data, to the noise of the data. How will this is our theory? How can we validate a result? And we have a priori estimates and a posteriori error estimate. So we are on a safe ground. So those are keywords that I'm sure in these corridors you know very well, and we have been hearing very many times. So well-posedness basically means that solution of the problem exists, is unique, and depends continuously on data. And this is correlated to the numerical analysis. So how stable is a numerical method? What does that mean, stability in this case? It means that you increase, basically, if you have a linear problem, if you increase the size of the numerical problem, your solution will not blow up. It will be uniformly bounded in a suitable norm. How can you quantify the uncertainty?
if you have uncertainty in the data or in the coefficients, how does this propagate into the solution, right? So those are classical questions that are very well addressed when you use a physics-based method, okay? Digital model. We like to replicate those, say, this setting when you use machine learning algorithm. And this is not obvious how to do it, but those are the guidelines, right? When I have a PDE. Now, you have a PDE, assume that it's a stationary PDE, you don't have time, independence, but this is not an issue. You want to use scientific machine learning and combine the two approaches when you have an intricate and multi-scale behavior of the solution. When the data sets are sparse and costly to obtain, it's very difficult to generate the data determined from the PDE, for instance. When the decision, this is extremely important, decisions carry significant consequences. For instance, your problem is a problem in medicine or in finance, and if you make, say, wrong decision, you may have very wrong and bad consequences, right? For your health or for your business, for your, say, welfare. We want to increase the predictive capacity of your method. You want to be able to provide the right interpretation of the results, which is very often not the case when there's machine learning algorithms. Interpretability is one of the big issues. Many times, algorithms work fantastically well, and other times the same algorithm in different circumstances do not work at all, and you don't know why. And for mathematicians, this is very bad, right? And you need domain expertise. So those are the contexts where the situations where you would like to take advantage of this. And I like to show two different approaches among the many approaches that you have seen on the two drops that were qualified. And the first approach is how you empower your training set by the order method, by numerical solution that you class. So this is the framework. You have a PDE, and for P of ZU equal to 0. Sorry, typically we use U to identify the solution. Here U is the set of data, Z is the solution. And then Y is the observation. Is what you want to observe. For instance, solve a fluid dynamics problem around an aircraft, but then what you want to observe is the drag and lift on the wing, for instance, right? You have a peak post-processing solution. So use the input. Could be parameters or functions. Z is the state, and Y is the output. So what is relevant here is the so-called data to solution map, right? M goes from U, the set of the space of data, into the space of observation. And you have a numerical model. I assume that you know everything about your PDE. So this is a PDE that you know that is a good model for your problem. You have a numerical model that you can write by putting, say, H everywhere, right? So you have a data distribution map, which is a numerical data distribution map, and H goes from U to the same set of data to one H. One H is the one that you get posteriori after solving this problem numerically. So this is also called high-fidelity fundamental model. Engineers use high-fidelity because they say that this is the best that you can do. How can you inject this into a machine learning algorithm? What you can do is to sample the set of input data. So you take 10 samples of the data. You compute by your high-fidelity model the corresponding observation. So you solve your PDE 10 times, compute your observation. Then you use this outputs UI and YHI as training set.
So is the exclusive training set, or is just an arrangement of the training set in place? You choose the hypothesis space. Maybe you remember yesterday that we did the equation here. This is the subspace. Okay, in the data-driven algorithm, I have data in a supervised learning. So I have observation. Sorry, I have input and label. Right. In this case, I have UI and AI. And I'm looking for a function that would likely describe the underlying behavior of this data. And again, it's an input-output function. So I need to find it in a suitable space that I called yesterday age. And remember, when I use my model, for instance, numerical artificial neural network, then it means that I'm sitting in this space, in this hypothesis space. So this hypothesis space, where I'm going to develop my model, and what I'm actually doing is taking the minimum of this argument, and this argument is the node suitable sense is a discrete node because I'm summing over all the data, the training data of the observation provided by full order model. This is what engineers call the ground truth, vérité absolue, minus what your scientific machine learning algorithm, your neural network in this case, will be. So you minimize this error, and by doing that, you find the parameter of the neural network that will then be used to define the network. So as you see in this case, the PDE is entering through its numerical solution to feed the training set, and then the hypothesis space will be selected by the machine learning algorithm by minimizing an error that will depend on this range. This is very fast, right? You use the PDE to feed your neural network. So if you have any information about the physics and you know the model and you have a corresponding high fidelity model for the solution, numerical solution, why not use it? Okay. Here is an example. I want to solve this problem. Of course, this is an academic problem, especially hard is an academic problem, just to show that you can work with this. So this is a two-dimensional, three-dimensional channel with two inflow boundaries and one outflow boundary. You can put typically the condition of the inflow boundary, you prescribe the velocity field of the flow, right? And the normal condition of the outflow boundary. So this is not a solid boundary, it's not a wall, it's just when you are dropping, cutting your channels. So use the Navier-Stokes equations, in this case, spanning Navier-Stokes equations inside. For those who do not know Navier-Stokes equations, those are minus the viscosity of the fluid and the Laplacian of the velocity field. V is a vector field. So this is the diffusion. This is the convection, is V dot gradient of V, which means that the transport is dictated by the velocity of the fluid itself, right? So this is a non-linear term, it's also called the inertial term. And then you have one more rho, this is fluid density times the gradient of the pressure, equal to 0 if you don't have any external source, external force. Then you have, so this is called the momentum equation, this is called the continuity equation. The values are equal to 0, means the fluid is incompressible, right? And then we have boundary conditions. So at the outflow, we put normal boundary conditions. This is the normal component of the stress. So it's minus mu normal derivative of V plus 1 over rho P, which is a scalar time n, which is a vector, Newton vector, pointing outside, equal to 0. And here, we want to parameterize our problem. We want to put, say, a profile here and there, which is represented by these two vector functions, but we want to decide the intensity of the profile, we want to let it free. So U1 and U2 is the intensity of the profile. So you want the strength of the stream and the inflow, right? And U1 and U2 are two parameters. So we want to describe the manifold of all possible solutions corresponding to each of these two parameters. Okay, that's the idea. So assume that you use a classical approach. We have a finite element solver. You have to solve this problem for every possible choice of mu1 and mu2s. So every time you have a full order solution. So this is very expensive. What is the goal here? The goal is to predict the value of the pressure everywhere when you change the intensity of your stream and the inflow. So when you change mu1 and mu2. So these are the set of parameters. These are the physical parameters, not the parameters of the right? So you use a full order model. You compute first of all, you sample your mu I. You take some samples, right? You know that the viscosity, I'm sorry, you want to compute here, in this case, a stream within a certain range, say, and then in that range, you sample your mu1 and mu2, and correspondingly you find your finite element pressure at all nodal values of the finite element. Okay? Yeah.
So it means in particular that you have to make an a priori choice for the samples. I mean, you can choose a compact, and of course the choice of this compact is very important.
Yeah, absolutely. And in general, there are many different possibilities here. There are many different criteria to sampling, say, the distribution of specific set of variables. That's a very typical problem. You go with model order reduction. You start from sampling your problem. Typically, you don't have only two parameters, you have many parameters, so sampling properly is important.
Sure. And how can you do when you don't have any a priori, say?
Well, if you don't
really know a priori.
A uniform distribution.
Okay.
But otherwise, if you want to pay a bit more, you use what is called a greedy algorithm, and typically, now you know, Yvonne here is the master. So what you can, for instance, do is assume you only have one parameter, just to simplify my solution, right? So this is your parameter. You know that this is the interval, so this is the mu mean, and this is mu max. So the trivial choice would be to sampling uniformly, but that's not necessarily a good choice. Remember that here we have an output, and the output would be P, right? So P is the out, and could be any, right? Yeah, so we have parameter and output, right? So the idea of the greedy algorithm is that you take the very first one without any criteria, put it everywhere, right? And so this is the very first one, the first. And then how do you choose the second one? You choose the second one in a way that the corresponding solution would be the farthest possible with respect to that one.
I see.
And so on and so forth. You pick the third one in a way that, say, the third solution would be very far from this and that. Of course, you need to have a scalar product to just quantify how far you are. And this is, in principle, this is an NP problem in the sense that this is extremely complex, because you should compute all possible solutions. See, mathematically speaking, this means that once you choose this one, you should compute all the possible solutions and then see which one is the furthest one. In fact, you have some numerical greedy algorithms that are based on a posteriori analysis that helps you in understanding, in finding, say, in devising the strategy, yes, in order to be cheap enough. But there are many different approaches, say, and that obviously they are not trivial, because the problem is very complicated. But if you don't have any idea, just spend it in a kind of uniform way. If you want to be lazy and not spend anything for that.
Thank you.
So you have to sample the space of the parameters and find the corresponding PI, right? The solution. In this case, the solution is the solution everywhere, the numerical solution everywhere. But as you might know, if you use finite elements, the solution everywhere is characterized by its value at the nodal point. So for those who are completely unaware of numerical analysis for PDEs and for the hierarchy method, assume that you have a one-dimensional problem and your solution is, you don't know what it is, right? Now what you do is to compute in the simplest possible case, an approximation of your solution, which is a piecewise linear function, and this piecewise linear function that we call UH, say, or pH in this case, right? This pH is characterized uniquely by its value at the nodal points. So it's vector of values that characterize completely your solution. So you start from a parameter and you end up with this vector, which is the corresponding set of solutions. So this, then mu I and pi is the training data. Okay, and you have very different approaches. This is one approach. The first approach is that you choose those parameters, you compute the corresponding solution in all possible nodes, right? By our, say, neural network. Okay, and the neural network has chosen its parameter W. The W are the parameters of the neural network now, right? By minimizing the discrepancy between what the finite element method, the full order method predict, and what the neural network has been predict. So you've been feeding your neural network by, say, finite element solution, full order solution. This is one possibility. The second possibility assumes that you are only interested in observing your solution at a specific set nodes, because engineers look at the how is the pressure at specific points in your domain that are affecting the pressure everywhere, for instance. So you put your, besides your parameters mu1 and mu2, you put the nodes, the points where you're interested in, where we want to observe, as further parameters of your network. And the result is the result only at those specific nodes. So you are very flexible with this experiment. The neural network digests that. The point is to decide whether or not in the end have a result of quality, but you can be extremely flexible in using them. There is no correspondence with having a well-posed program. You can take 2 nodes, 3 nodes, 100 nodes, and computing the pressure in those nodes or everywhere, it does not matter. So those are okay. So here are 2 examples where you can actually use high order finite element method, say full order method like finite elements, to feed the neural network. These are completely different kind. Yeah.
What is the efficiency of such a process compared to the POD method or something?
POD provides the philosophy is the same, but the difference is that when you use a POD method, you
compute on a course grid or something like that, some charts, and then you decompose on this chart.
So if you use a reduced basis method, which is a smart mathematical way to use POD, say, what you do is that the first step is the same, we send the sampling is the same, with the same criterion. This is what you do offline. So,
yes, but you can do that on a course grid, for example.
You can do it, any criterion you may have, you can use it, right? However, if you use it in a course grid, then the result in the end will not be comparable in terms of accuracy with what you obtain in final.
Then you have
balance.
Instead of having basis, classical basis of finite elements, you have this chart of course grid simulations.
Yeah, sure. But okay, what is your if you're interested to find something which has an accuracy comparable to that of finite elements, right? Then you have to be extremely careful in how to select, how you sample, and then what to do after sample. So the first step is sample and compute the corresponding solution. This is what you typically do offline, once and for all. The second step is that now you change my parameters in one to two. I want to compute the solution online. What do you do here? What I've been presenting here is use a neural network to do it. Okay. The alternative approach, one alternative approach, you use basis method, you compute the sampling, you compute the corresponding solution, and instead of using a finite element space, which has a dimension equal to the number of dollar points, the finite element space with dimension is the number of sampling solutions. So just use 10 μi sampling, you have correspondingly 10 finite element solutions, and then you look for a linear combination of those finite element solutions. So your local problem will be, again, solving the Galerkin problem, the PDE, but on a much lower dimensional space, while here, the problem is that you are not solving the PDE, you solve the neural network online. So this is the basic difference, right? So here you solve the neural network. And of course, here you gain in terms of flexibility, there you gain in terms of accuracy and interpretability. Because you have a complete, I would say, error analysis when you use a use-basis method. When use-basis method, basically you only solve Galerkin method. Once offline and the other time online on a much lower dimensional space. While here you are in the realm of neural network, you can do whatever you want, basically, many more possibilities. So this is a completely different approach. I would say it's a kind of dual approach, not speaking in the sense of mathematics, right? You don't have your spaces, but just give you the idea that there are different way to create this interplay. And this is say the PINN philosophy. PINN stands for physics informed neural network. So again, you have a neural network, but you want to inform it with the physics, but not through the training data, but through the equation itself. You want your method to know what is the equation behind. Of course, if you know the equation behind, if you don't know the equation behind, just use neural networks. Okay. So what is the idea? Well, this is page 1 of any PD numerical analysis, right? So in this lab, I think that people like Jean-Pierre and François have seen it zillions of times, right? So Laplacian, just to explain something very simple. You have a Laplace equation with say normal conditions, and actually may start many kinds of problems. Just to take this, right? So what you do if you want to stay in the physical setting, you just write it with. So you look for a solution in this solar space, which is called H1, with the L2 norm and the L2 norm of the gradient, so with solution in L2 and the gradient in L2 as well. And you look for the bilinear form, see A over V, which is after integration of parts in the integral gradient of U gradient of E plus gamma UV. And on the right hand side, you have the forcing term multiplied by V, and what you get after integration. So you have G, which is the normal derivative, and V is the test. So find U in V such that A of V is equal to F of V for V. This is the classical liturgy of PD numerical analysis in France, where everybody start from valuation of principles. You go to an industry, they will typically use finite bodies, so it's a completely different story. But here, so this is the problem. Then, of course, you approximate it and use the Galerkin method. The Galerkin method basically means that you project this upon a subspace. Right. And the subspace can be made by any type of functions. It should be a closed subspace and the finite dimensional space. And so you end up with something like this, find UH in VH, VH is the subspace. You parameterize it with H because typically you think of a mesh, and when you think of a mesh, you think of this H here, which is typical size, say, of the subinterest in 1D. And of course, in 2D, it will be triangles, and 3D, it will be tetrahedra, and so on and so forth. So this is the Galerkin method. There's not yet a finite element method. Finite element method comes later, depending upon the choice of the UH. Right? If VH now is a piecewise linear function, set of piecewise linear function, like in this case, then this should be a Galerkin finite element. But in general, for the Galerkin method, this is all very elementary, but I want to bring your attention to this point. when you choose a basis function for this finite dimensional space, you look for a solution in which is a linear combination of uj dot vj. Vj are the basis function, and uj as the coefficient, unknown coefficient, right? So if you find these unknown coefficients, A and B, I don't know why there is H here and B here, but it's the same image. So if you find this uj, you find the complete information solution. How do you find uj? Well, you take here instead of any arbitrary function, you take the element of the basis function. So you have NH equations, and those NH equations provide a system of algebraic equations. The derivatives have gone because the derivatives are encoded into this linear form A, and so this linear form is actually a matrix because you have two indices, and this is a vector, and this is a vector. This is the right hand side given quantities. Those are given, you compute that given, because the Vj are given, and Uj are there. So it's a linear system. Okay. So you solve this linear system under the form A and U equals to B, and you get it. If you don't know this, you don't have the limit to stay in this. So what is this basis function? The basis function is when in a 2D you are this Pj, these are associated with nodes, and nodes vertices. The vertices for every basis function, for every node you have a function which takes value 1, with the piecewise linear function that goes to 0 in all other nodes. So you have pyramidal functions. Right. And this is a typical solution that you get, it's a piecewise linear solution. Okay, so everything very, very straightforward. So these are finite elements, and let's try to see there are some analogies before. So there are different types of words, right? So neural networks are finite elements. Here we work on the random setting with very clear seeds, solid spaces. And then for dimensional spaces and projection, scalar products, and so on and so forth. There you just take a track and use you see minimize coefficients that what done when solving there. This is what escape our understanding. But in fact, you can find some analogies. For instance, let us interpret finite element, right? VH. The input, which is space, not H1, but the say Euclidean space, so Euclidean solution. And you have these quantities here that are your unknown, and you can call that breakout quantities. After all, when you solve a division neural network, you are training your model to find the parameters. And here you are solving the same type of philosophy. The difference is that there you do it by minimization, and here you do it by solving the system, but those are trivial parameters. And if you use an architecture of, say, feed-forward numerical neural network, you have a similar interpretation. You are looking for a solution, which is the solution provided by the neural network that depends on X and parameters. Those are the parameters of the neural network. So why not using V and N as a trial solution space for a PDE? What is a trial solution space? Well, you have your PDE that you write A of V, so look for U in capital V, such that A of V is equal to that of V, right? Oh, and V in capital V. Well, when you have a hierarchy method, you have UH in VH, such that A of UH, VH is equal to F of VH. For every VH in VH, I just see. Actually, you can do something a bit more general. You can use this as a different space. Okay, so this is called the trial space, trial, where you look for your solution. And this is called the test space, test. Right? So instead of using this trial space, which is the current element space, why not using this? I mean, I'm looking for a solution which is a neural network solution in a Galerkin setting. Yeah, well, unless the POD you compute a high order solution that you let your correlation matrix work for you, and but yeah, of course, yeah, it's a matter of time. So these days, motivations. Is this a good idea? Do we have advantage or disadvantages? Well, neural networks are very efficient in approximating functions. I don't remember if I've shown you these convergence results for neural networks in general, but you have results now that show that neural networks are very good in approximating continuous functions, any kind of continuous functions, but also if you have extra regularity, you can extract more accuracy. They are measures. This is a very important point. They are measures in the sense that you don't see the mesh. The mesh in 1D is not an issue, 2D, not really, 3D might be an issue. If you use finite elements or finite volumes or spectral methods, you have a mesh. And creating a mesh is very critical. So if your domain is very complex, shouldn't you want to solve the problem around an aircraft or a car? Of course, the domain, the stereo domain is very complex, and then creating the meshes takes forever. Also for the hard, you have seen the meshes that we're using is extremely complicated, right? So these meshes, you don't see the mesh, right? However, these neural networks, they're not linear. I mean, the dependence of the parameters is not linear. You remember the activation function that you have in the neural network. Activation function is not linear, and then always they are non linear, even though your initial probe is your original probe is linear. Right? So you have a nonlinear approximation of a linear problem, and so the Galerkin method cannot be applied as is. So the idea would be to use this new trial space instead of this one, but Galerkin method is a linear problem. Is a linear method because it's projection, right? So it's a linear problem. It's a linear approach, right? But here we're talking about nonlinear. So once we have understood the analogy, we start seeing that the analogies cannot continue forever, right? There's a limit. Okay. So here is where the pins enter into the Séminaire say. So what is the idea? The idea is somehow simple or obvious, obviously a posteriori. Right? All the great ideas a posteriori look very simple. Because simplicity is a way to generality. If something is simple, you can interpret it and then change your program and you see easily how to extend it. If you have something which is a method which is very involved also for a very simple program, then maybe is a niche application, but then you want to generalize it is a pain. Okay? So how does it work? Let us go back to our original, to our Laplace, and forget about the weak formulation of Laplace, variation of formulation, the one that we love, right? Let's stick with the strong formulation of Laplace. So you use the two second order derivatives. And let us formally speaking, define a residual. What is a residual of the PDE? Well, residual what remains, right, is the difference between left and right. So if this is the exact solution, the residual is equal to 0. If you use the exact solution. If it is not the exact solution, well, the residual tells you, the features tend to depart from the exact solution in a suitable quote norm dual. Okay? Then let's take also the residual for the boundary conditions. maybe the boundary conditions are not satisfied exactly. So you take the residual also the boundary conditions. Okay. And then what you do? Well, you use a neural net to solve your problem, which means that we have input parameters. You feed your neural network in this training set. You end up with your solution. Remember, neural network is data to solution map. Okay, so it will find, the neural network will find a solution in the set of points that we set up the right? Now we are assuming that we can manipulate this solution to compute the Laplacian derivatives, gamma time u, or the normal derivative of something. So you go back in history where we're using finite differences and to take all the limits. But you'll see that this is easy. But I assume that you can do it. Then with this, it is a post-processing. We're not solving it, we're just computing. With this, you can compute the residual of the PDE and the residual of the boundary conditions. And of course, this not be zero, because there's no way that your numerical, say, neural net will produce an exact solution of the problem. That would be fast. So you have those residuals, and use those residuals to feed your loss function. So when I use a neural network, the parameters are used are obtained by minimizing the loss function. Remember? And here I'm changing my loss function by adding not only the part that I would consider from a neural network. Remember, this is the one that measures the discrepancies from the predicted value of the neural network and the ground truth when we have a supervised learning. I also had a term that depends on the residual of the PDE and the residual of the boundary conditions times suitable coefficients. Okay, I'm weighting in a different way if you want the residual of the PDE and the residual of the boundary conditions. Yeah.
So here is the input that have don't contain the exact boundary solution, boundary condition.
The input is whatever you want to put there, right? So assume that you have a boundary condition, that you know the boundary condition is very few points.
If we know the exact boundary condition, we put it as the input data, the reduce the solution, to produce the solution, won't be exactly have the same value.
Not necessarily. When you it depends where you measure this. If you measure the residual at the same point, then of course that will not contribute to the residual, will have zero. But if you want to measure the residual in another point, because you know the boundary conditions in maybe just in should have your channel. Maybe you only measure the velocity in one specific point at the entrance of your then of course you may have a discrepancy. So the residual, depending upon where you compute your residual, which are the points where you measure the residual of the PDE or of the boundary conditions, well, you can match exactly or inexactly the possible boundary condition to be.
Here, W is the parameter for the neural.
For the neural network, yes.
If you use your neural network this way, it's not really meshless. No?
Sorry, if I use
If you use it this way, you have the mesh hidden in the collocation points, no?
yeah, you have
It's not meshless.
it's not actually it's not a mesh. Mesh means that you need to create a partition of your domain using substructures like triangles or tetrahedron. Here, this part is missing. You may have points, right? But those are not points on the mesh. Those are points where you measure your residual, for instance. So you don't have to create a triangulation. That's the point, which is a very expensive part of the story.
Then you have to compute minus what the.
Sorry? Say again?
You have to compute the operator on
Yes,
this point.
but this is but this is not,
So who are the neighbors of one point and so on.
you don't care about this because you use automatic differentiation. So this is from the algorithmic point of view, that's the big thing. Or if you want, assume that you want to use, you have to compute derivatives of information points, and you want to use local Taylor formula. And then in that case, you will need to know where they are the other points. Here use automatic differentiation. So you can get this information, I would say, basically for free in terms of computation. Restriction is that you use an activation function, which is good, smooth. So not the stepwise, but for instance the arctangent. And then you need to minimize the local. So even if you start from a linear problem, you have to solve by minimization algorithm. So trying to put the plus and the minus in the unit systems. Now, how do you choose the collocation points? Collocation points means where you're actually evaluating your residual. Could be on boundary or the boundary residual, to which extent I'm satisfying the normal boundary condition, or the internal points where I'm actually computing the residual of my PD. So you have points in the boundary and points in the residual. And here you can use different approaches. You can use Monte Carlo quadrature. So you take the distribution of your points, more or less regular distribution of your points. And this is very easy. It's not that accurate because you know that if you compute an integral by Monte Carlo, in the average, what you get is an error which behaves like 1/n, the number of points that you're using, square root of. So the convergence with the total number of points is very low. So it's a good, Monte Carlo is good, very expensive, but also it's low to converge. Alternative, you can do something more sophisticated. In that case, you can use quadrature formulas. For instance, you can use Gaussian quadrature formulas to ensure points. And in that case, you have more points, you use activity. Your solution will be more accurate. We tend to 0 as 1/n to the power s, where s is the hypothetical solid regularity of your exact solution. And you don't necessarily know. But assume that your problem behind this is a good problem. The sense that the data are forcing term boundary conditions. So your real figure are regular, then you would expect a high regularity of your solution. And in that case, you need to pay off to use say collocation methods, the Gaussian methods. Okay. So one possibility is to use variational P. We have been using the strong form of the equation, remember? The residual strong form of the equation. But sometimes the strong form of the equation does not make too much sense. For instance, if you have a shock wave problem, you have, say, nonlinear conservation laws. How do you compute the exact derivatives? First order derivatives. The first order derivative does not exist in a C0 sense, right? So that's the reason why, since Lerey, since Schwartz, they've been developing the variational formulation forms afterward. But you can still try to modify the previous approach with a sort of variational formulation. And actually, in this case, you remember that I told you before that you can use a set of function here and a set of function there that can be different. Those are the trial and those are the test. So here the idea is to use a trial function that are those dictated by the neural network, because the solution will be a neural network solution. And the test function will be the finite element spaces. And you can use this type of approach. And this is used to compute the residuals. Instead of computing the residuals pointwise, you compute the residuals locally. Say this variational form. And these are called variational forms. Then there are other, say, other variants as well. So, is it the iguana, the pins? I mean, is it the fantastic answer to all the problems? No, not necessarily. They are their weaknesses and their strengths, pins, weaknesses. You need to solve an optimization problem. And I already mentioned this, even when the partial differential equation is linear. If this is very important, use a different color because I want this message to be very clear, very valid. You have to solve the PDE. If you know the PDE and you have to solve it once numerically, just go with the lurking current element. You cannot beat it in terms of computational efficiency, in terms of accuracy, or any other lurking method. Yes. So this is not a way to say gain in terms of the standard approach if you have to solve it just once. Okay. Of course, if you have to parameterize your problem, then is a different story. You have to compute it very many times. Or if you have a control problem where you have to go under, say, an iterative method, then it's a different story. But for a single shot, don't use it. A new training for each instance of the data is required. Training is the loss weight, the weight you remember that they put in front of the residual, alpha, B, C, and me. Those coefficients. Of course, you should have to train also the coefficients, because of our hyperparameters is an issue. They often show lack of convergence. I don't know why. Sorry. They tend to learn more easily the lower frequencies of the solution. There are solutions that oscillate a lot. For instance, they tend to learn very easily the low frequency of the solution, the low frequency components of the solution, but they are not as good in the higher frequencies. And if you don't use the variational peak, use the classical residual, as I was saying before, not always your physical problem can be written in the strong differential term, right? And I mentioned before for example, the lack of first order derivatives or second order derivatives is if you take an elasticity problem with data that are not good enough. The strengths, well, you can use that even if you don't have boundary conditions, so enough boundary conditions or initial conditions or coefficients. So in that case, you'll be stuck with finite elements with standard approaches. There you can use it, right? And sometimes, if you're an engineer or experimentalist, you don't even know that there are various observations behind. Sure that you don't know, you just went through problem and you just use particle velocity to measure quantities. You have those quantities and you can use them as training parameters in order to train your I told you that it's mesh free, you don't have to create a mesh, but this is a bit more tricky. There are open source tools now based on deep learning, neural network, deep neural network that allows you to implement things. I'm not saying easy, but relatively easily. They are affecting this molded regime. And at some extent, you can extrapolate your solution more successfully than using finite elements. Extrapolate your solution beyond the data more PDEs. So, extrapolate the finite element, and you see it here, right? So, this is an interval 0,1. We're solving a certain problem. I assume that actually my problem, this is a bar. Assume that the bar instead of being a length 1 is a length 2, right? So you know that there is a solution also here. Can I extrapolate these values? Does not make any sense because the extrapolation can only depend on the last two values, completely forgetting the history. So extrapolating when you use piecewise linear elements, piecewise quadratic elements is not a good deal. It's not a good idea. With this, I mean, you can be more successful in extrapolation. So you see, it's you have to be careful. You have to be careful, and this is very much as usual, problem dependent. There are other approaches, actually there are many other approaches. I will not talk about it because of time. When you want to use in a combined manner PDEs and the say digital models and artificial neural network. There is a general family which is called operator learning. You just have data and you like to infer which PDE is behind. And that's a big issue, right? Not the PDE, just that data that have been generated by a physical program that has that PDE that is kind. Sure that you don't know the integration back in the history, right? But you have a fusion problem, so you have data. So you have source third, and then you have the temperature, for instance. Can I infer an operator which is behind this? But before doing that, let me talk about what is called neural operators. Neural operators are these are terminal literature. Neural operators are operators hidden by the neural network. As you remember, the neural network is just a set of neurons, and each neuron receives information from the nearby neurons. They make linear combination, and then they add a bias, and then they have activation function. So all this is discrete, right? Just working on discrete quantities. Can you generalize it to functions? And this is what they do actually. So the idea is that instead of multiplying coefficients by weights and adding a bias in a discrete manner, you write this process as being the integral of omega. Of course, if you're solving the problem, PDE problem omega, right, of a certain kernel multiplied by V plus B bias, and those are functions. So you can create a neural network that is capable of producing functions instead of single segment values in the output. Then you can generalize this. And here you can use Fourier transform and inverse Fourier transform instead of Kerr. So in that case, you call neural Fourier neural operators. So we are generalizing the issue here. And the last idea, as I mentioned before, I'd like to address here is trying to learn the operator, which is behind an equation. And this is something that has been investigated by several people, in particular by Siddharth Mishra at ETH. And now it's very technical to show, so I'm not do it. But what is funny and is also a bit surprising is that you can train your network using 3 or 4 different operators to generate the data, feeding your and then you can be, well, actually he is able to show that you can reproduce the solution of other processes which is run by different operators. Say, use the plus equation or and the Navier-Stokes equations and the equation of linear elasticity to train, and we can generate an operator which describes Maxwell equations or Euler equations. So you can extrapolate with respect to the training to the type of operator that you've been using for the case. And what to me is very remarkable is that the kind of neural network that we are inspired by those that are used for the large language models. So it's, I mean, is that to me it's a new world. You find things that are unexpected, and in the end, at the end of the day, you know, if you have many data that are arising from measures from a physical problem, those data bring knowledge. And the point is how to let this knowledge to pop up. If you can couple it with the knowledge on the PDEs or physics, you have a new tool to generate new knowledge. Or that's my interpretation of the story. I have a few more minutes. I would like to show you 4 or 5 pictures, actually not pictures, algorithms, just to let you know that what I've been talking about before is not only kept at the mathematical level, but we've been actually using it to solve problems, some of the problems that we have with our health simulator. So here is one example. Here we use pins, actually use multi-fidelity pins. So we use pins with different type of fidelity or accuracy in an embedded way to estimate the ionic parameters. Maybe you remember that when we solve our problem, we have in particular to compute the dynamics of the ion at the cell level of the cardiomyocytes. And so you have something like this. So these are cells, those are channels that open and close. And you have species that are here that migrate outside and other species that migrate east. And this is change of ions. This creates the same force, the active force, that's the potential. The cell potential is an active force, and that is the one responsible for the contraction and relaxation of the cardiomyocytes. The point is that these dynamics is governed by a set of coordinate differential equations. So here you have v of say I over dt equal to f of I. I are the ionic species, calcium, phosphorus, potassium, and so on and so forth. And you want to see the dynamics. Those are similar to a single point in space. So there's no space dimension here, right? Because those are microscopical. And actually, we virtually identify those points with the finite element points where we solve our problem. Okay. So these depends on many parameters, which are characteristic of the specific cell behavior, which of course depends on specific individual. So how do you find them? No way to get them from medical investigation. Of course, you should go to the microscopic. So do that. So we use pins to do that. The neural network, and we feed them with an ordinary differential equation. And what is important is that we end up with getting results that are not good enough. Without artificial neural network, here will be stuff. Because we know the model. For this, there are very many different models. So there are phenomenological in these cases, very particular models for the bueno obvio model, and but we don't know the coefficients. So we use the pins to get this. This is another problem. This is the classical problem in electrophysiology. The impression that your heart is not working properly, the very first thing to do is go to a hospital and go in take ECG, electrocardiogram. Electrocardiogram means that they put some lead in your body and measure the potential, the waves, wavelets, the electric potential in the body, say, then the doctors, by looking at this, should be able to infer the behavioral path, which is not on the surface, right? So mathematically speaking, is an inverse problem. So you have information on the surface of the body, and you want to retrieve information in the interior, where you have the heart. Right? So you have the heart, and the body, you have information on the body, some part of the body, and you have to retrieve information in the heart itself. Those are inverse problem. Of course, inverse problems are imposed in condition from the numerical point of view, they are nightmare. And to solve an inverse problem, you have to iterate so many times the direct law or the physiology. The direct problem is the one that you solve in the heart, generate a potential, and let the potential propagate through the torso. So it's extreme expense. Right. So here we use physics in 4 neural network to solve this problem. It should be otherwise impossible. I'm not giving you the details, but I mean the details are somehow contained the or a corollary what I represented before as general structures. And this is a very critical issue. I told you many times that the active force is the one that is generated here at the cell level and microscopic level, and there is no ground truth. There is no universal law of nature that allows you to find this active force, and yet it is extremely important. So we derive it by neural network. Deriving by neural network does not mean that you find a specific formula, simply means that you find the way it is said. It's always an input to output. Right? The output is the strain of the cell, and the input are information on their own parameters, right? And the extracellular potential. Right? Okay, here is yet another issue, but and then I'll conclude this example. I think that I have been trained, as many people here, with the dream of result solution. We want to approximate result solution. We, the mathematician, tend to believe that mathematics is an exact science, right? Which is perhaps true, perhaps. Not always, but practically speaking, this is absolutely irrelevant. Unless you are working on a discrete setting. If I had to count how many people are in this room, if the answer is 22, and they say 21, my answer is wrong. We're working on a discrete setting. If I measure the temperature of this room, and the precise answer is just guess 22.355, and they say 22.3 is more than enough. But the accuracy is induced by the relevance of the result, right? So there is nothing more wrong than pretending having result solutions in applied mathematics. That's my personal opinion. It's what I experience all the time. Right? In particular, the dream of providing a solution to a PD, a global solution might be global, I mean, at any point, is beautiful, but very often is not actually what you need. So when you solve it, just to go from the general statement to practice statement, when you want to solve an applied problem, what counts is the opinion of your counterpart. The one that said the question. If he's a doctor, if he's an engineer, if he's a, you see, yachtman, if he's the coach of football team of your city, this is what counts. Because this is the way, this is what he's going to do with on. Okay, so you have to please him or her by delivering the solution with the accuracy that she needs interest. So in particular, for the R, where you have all those equations and all those variables, those unknowns, mean, it never happened to me that the doctor asked me give delivery to complete set of solutions. It interests in one specific thing, in some specific thing. So your medical method should be driven by that specific answer. So always goal oriented in a time map. This is my personal opinion. Always goal oriented. So in particular, doctors know very well this type of this theoretical curve. Every doctor, right? They know anything about mathematics, indeed, but they also know this. What is this? This is the volume to pressure. They call it pressure volume loop. What does that mean? Well, take a ventricle. Don't take the whole arm. Take a ventricle, right? Ventricle is relaxing and compressing. Okay. So the volume will change. And the point is, at which extent the pressure of blood, the average pressure, will change depending upon the volume. So when a doctor look at this, it will immediately understand if this work, if this curve, if this R is working or not. For instance, the distance between this is time, right? So fix a given time. The distance between this point and that point, this distance here. This is a stroke volume. Stroke volume means the volume of blood that is ejected in a single heartbeat. And this is very important because if this is not enough, you know that you're going to have problems. Just to make an example. So PD loop is clear to everyone. So why not providing the PD loop? Right? Democratizing your science. This is something extremely important. And therefore you tune all your algorithm, your model, in order to be accurate on this answer. And maybe completely wrong on the electric potential. But this is not the goal. Okay? So if we use reduced order models to compute the electromechanical model, which we take otherwise forever, for hours, right? We can go and reduce it at the order of a few minutes or sometimes a few seconds, and still being accurate to provide that specific answer, if you think that this is relevant to your content. And I would say that all what we are doing, besides developing this big hard model, which is very rich and very accurate to describe the complete activity of the art, actually when we are, let's say, collaborating with doctors, all what we're doing is very much driven by their question. So we have to reduce the whole thing, what is necessary to provide the accurate answer to one specific question or to two specific questions. So this is a goal-driven mathematics. It's not mathematics with a big gun that you use for every possible problem. This is fine, curiosity-driven. You have to create knowledge, but when you use it, it's goal-oriented. I'm late. I'm going to stop here. I have many other examples, but for those who be interested in some of the say the algorithm that have been the methods that have been discussing, they are published, and you can actually find them. In particular, this should be in my lecture notes, so you no need for you to take a picture now. Later on in the lecture notes.
Thank you so much. Merci et bravo, Alfio. Congratulations for these lessons. Are there some questions on what Alfio said? Jean-Pierre.
So you essentially use the neural networks for sub-problems, or you have...
In principle, you can use it for the whole problem, right?
You're not interested in that.
No, it's not that I'm not interested. Of course, it's much more expensive, and the quality of the result. I mean, if I use standard methods, as I did in the very first lecture, I can also have an appreciation of the quality of the result. So everything is more or less, everything is unknown. I'm saying more or less because for the complete problem, we don't even have an analytical result. I mean, result from analysis. That problem, we don't even know if you have well poisons for the old problem. You have well poisons for some problems, but not for the old problem. Without to have an consistency with this result, but this is missing. So one typical question that people may ask, why are you directly solving the problem if you don't even know the solution? In this case, my answer is that we are living guys, so there should be a solution. It should be unique.
But for example, you take this vertical question, the difference of volume,
Yeah, the PV.
and the doctor says, oh,
There's a problem here.
there is a problem here.
Yeah.
There is not
There's a problem because
enough,
the picture is not the one that is expected then, of course.
okay? How to try to know why? No.
Okay. Okay, that's a different story. So this is the difference between diagnosis and understanding, and then therapy, right? So this is what you do with mathematicians. We find something wrong, and if we know the laws that are behind,
But if you have a coupling between the electricity problem and
Yeah.
the elastic, you can know maybe the elasticity
Yeah.
of the tissue
Yeah,
is not correct, or the electricity
yeah,
problem.
no, this is very important. This is very important. So this is the principle of causality. We, the scientists, sorry, I should not say we the scientists, because some doctors are scientists. So we mathematicians and physicists, especially we mathematicians, and we are driven by the principle of causality. If we translate it into PE terms, we know that if we change coefficients or right-hand side or boundary condition, you know what kind of variation your solution should expect because you have a priori estimates, right? So you know the role of variation. And we also have the sense of coupling. So you have two different equations that are coupled together. You know that if you decouple them, you make mistakes. If you are good in estimating the discrepancy in so there, you know that there is a memory, right? Now, this is somehow against the principle of spatialization. And yesterday, during lunch, was talking about this, and quoting some examples of elections that we learn in teachers and teachers. For instance, for disturbances in the algorithm, we can believe that this is only going to be a result of path. And in fact, you can see that some cases, the fluid dynamics part take a very big role in sustaining that type of say pathology, for instance, of fibrillation, right? Or again, you know that the mechanics is important because there is a mechanical feedback on the electrophysiology, which is typically disregarded to the clinical development. But you see that when you count it, you see it. So what you try to do is to provide solutions that are ideally they should be simplified, but at least reasonable, right? And on the basis of the solution, and then we start the discussion, and then by this helps for a better understanding what's going on. And in some cases, to say put under discussion their belief, because the reality is much more complex than the reduction to their single components. So this is what I believe is this is where there is a role for mathematicians. Because we tend to be holistic. We tend to put as much as possible in terms of knowledge into our models.
Thank you. Other questions or comments? No? Otherwise, again, Alfio, we thank you so much. Let me recall that tomorrow at 2 o'clock, there will be a colloquium of Alfio Quarteroni in place of the usual Séminaire.
Here.
Here, yes.
For those who have been attending, I will, some extent, I will at least half of my colloquy will be a synthetic representation of what I've been doing, but then will be also something that I didn't have the time to go through, and but I mean, don't expect something completely new, completely different.
What? You have until tomorrow. Thank you again. Thank you, Alfio.
I have a limited capability of learning in such a short time.